Welcome to today's exploration. We invite you to join us as we uncover the remarkable stories behind the small inventions that continue to define and enhance our modern existence. Do you remember using paper maps before GPS navigation? Have you ever been sent to the wrong location by a GPS? What was your first GPS device? Do you prefer a car navigation system or smartphone apps like Google Maps? Do you think drivers today rely too much on GPS?
Imagine driving to an important meeting. Your navigation says, "Turn right." You follow it, but suddenly, the road ends. A dead end. Your GPS calmly says, "You have arrived at your destination." But there's nothing there. No house. No building. Just trees, out to be a field or a closed gate, or a dead-end road. Believe it or not, a member of my own family experienced a similar mishap. On one occasion, his GPS confidently announced they had reached their destination, yet they found themselves facing nothing but a dead-end road. Hearing that story led me to wonder, what were the true origins of this technology? This happened to thousands of drivers when GPS navigation first appeared. A spinning circle appears on screen. An electronic voice drones. Searching for a position, searching for a position. That sound was the nightmare of the early 2000s. You'd be at a six-way intersection, and the GPS would just give up. It was searching for a position while you were searching for your sanity. Early navigation systems and even modern apps sometimes rely on map data that may be outdated or incomplete. Apps like Google Maps or Waze improve this by constantly updating maps using user reports and satellite positioning from the Global Positioning System. Today, we trust GPS every day. It guides airplanes, ships, and millions of cars around the world. While we now take the seamless blue dot on our smartphones for granted, the journey to modern GPS was a century-long saga of strange inventions, mechanical scrolls, and brilliant engineering. But the story of car navigation is full of surprising inventions, strange mistakes, and brilliant engineering. For centuries, travelers faced a simple but frustrating problem: finding the right road. Before modern navigation systems, drivers often relied on folded paper maps, roadside signs, and sometimes even stopped to ask strangers for directions. Getting lost was part of the journey. But today, many drivers simply follow a voice that calmly says, "Turn left in 300 feet." This remarkable convenience is made possible by car GPS navigation systems, a technology that combines satellites, computers, and digital maps. But how did this technology begin? The journey to this technology began long before satellites, smartphones, or digital maps existed. And why did early GPS systems sometimes send drivers to the wrong place, or even to a dead-end road? The story begins long before satellites existed. Early attempts to help drivers navigate. In the early 20th century, automobiles were becoming increasingly popular. As more people began traveling by car, a new challenge appeared: navigation. Road maps existed, but they were often difficult to read while driving. Engineers began searching for ways to make navigation easier. It begins with a simple question: how do you help drivers find their way? One of the earliest attempts came from Italy in 1932, when inventors introduced a mechanical navigation device called ITER AVTO. This device looked somewhat like a small dashboard box containing a scroll of paper maps. The map moved automatically as the car traveled, using a connection to the vehicle's speedometer. As the car moved forward, the map scrolled forward as well, showing the upcoming road. It was an ingenious idea. However, it had a major limitation. If the driver made a wrong turn, the map would no longer match the road. The driver had to stop and manually adjust the map. Despite its limitations, ITER AVTO represented an early step toward modern navigation systems. Nearly 50 years later, engineers in Japan developed the first true electronic car navigation system. In 1981, the automobile company Honda introduced a remarkable invention called the Honda Electrogyrocator. This device appeared in certain models of the Honda Accord and was developed together with the electronics company Alpine. Unlike modern GPS systems, the electrogyrocator did not rely on satellites. Instead, it used a method called dead reckoning. Dead reckoning calculates position by measuring how far and in which direction a vehicle travels. The system used several components: a gyroscope to detect direction, sensors connected to the wheels to measure distance, a small screen displaying a map. Drivers placed transparent map sheets over the display screen. As the car moved, a small dot on the map showed the vehicle's position. It was one of the first times drivers could see their position on a moving map inside the car. But the system had problems. It was extremely expensive for the time, costing thousands of dollars. It also required drivers to change physical map sheets for different regions. And over long distances, the system sometimes became inaccurate because small measurement errors could accumulate. Still, it was an important milestone. During the 1980s, engineers in the United States were also experimenting with digital navigation systems. One of the most important developments came from a company called ITAC, founded in California. In 1985, ITAC introduced the ITAC Navigator, one of the first digital car navigation systems. Unlike earlier systems that used physical map sheets, the ITAC Navigator stored digital maps on cassette tapes. A small computer inside the device processed the data and displayed the vehicle's position on a screen. This was revolutionary. For the first time, drivers could see a digital map that updated as they moved. However, the system still relied mainly on dead reckoning rather than satellites. Because of this, small errors could still build up over time. The arrival of satellite navigation. The real revolution began with the development of the Global Positioning System, commonly known as GPS. It was created by the United States Department of Defense during the 1970s and 1980s. The system used a network of satellites orbiting Earth to determine precise positions on the planet's surface. Initially, GPS was designed for military use. But in the 1990s, the technology gradually became available for civilian applications. This opened the door for the first true satellite-based car navigation systems. One of the earliest vehicles to include GPS navigation was the Mazda Yunos Cosmo, introduced in Japan during the early 1990s. For the first time, cars could determine their location directly from satellites. Navigation accuracy improved dramatically. Portable GPS devices. By the late 1990s, GPS technology became more affordable and widely available. Companies such as Garmin began producing portable navigation devices designed specifically for drivers. In 1998, Garmin released the Street Pilot, one of the first portable GPS devices for automobiles. Drivers could attach the device to their dashboard and receive turn-by-turn directions. Soon, companies like TomTom also entered the market. By the early 2000s, portable GPS devices had become extremely popular. Millions of drivers relied on them for everyday travel. Problems with early GPS navigation. Despite the impressive technology, early GPS systems were not perfect. Many drivers experienced unexpected problems. Sometimes, GPS systems directed drivers to the wrong address. This happened because digital maps were still incomplete or outdated. Other times, drivers were directed onto roads that no longer existed or into dead-end streets. In some cases, drivers followed GPS instructions into dangerous areas or remote locations. GPS signals could also be lost in tunnels, mountains, or dense cities filled with tall buildings. Despite these challenges, GPS technology continued to improve rapidly. Navigation in the smartphone era. Today, GPS navigation is more powerful than ever. Modern systems combine satellite positioning with real-time internet data. Smartphone apps such as Google Maps and Waze constantly update road information, traffic conditions, and construction alerts. Drivers can receive voice directions, traffic warnings, and automatic route adjustments. What once required expensive hardware is now available to nearly anyone with a smartphone. Beyond the blue location dot on a modern screen lies a sophisticated web of orbital technology known as GNSS, Global Navigation Satellite Systems. While the term GPS has become embedded in everyday language as a synonym for satellite navigation, it is, in fact, only one component of a much larger global puzzle. What is GNSS, the universal umbrella? GNSS is the comprehensive term encompassing multiple satellite constellations operated by various nations and regions. These systems transmit signals to billions of devices to calculate precise coordinates, velocity, and time. Today, a standard smartphone does not rely on a single source. It taps into a hybrid network of these systems to ensure accuracy regardless of geographic location. The 4 pillars of global navigation. The current landscape of satellite navigation is defined by 4 major international systems. GNSS is the umbrella term, encompassing multiple satellite constellations operated by different regions: GPS, US, Galileo, EU, GLONASS, Russia, and BeiDou, China. Your smartphone or wireless device likely uses more than one of these systems at once, tapping into a hybrid GNSS network to ensure you're always accurately positioned, no matter where you are in the world. So, if you've ever looked at a location pin on your phone and thought, GPS did that? GPS, or the Global Positioning System, was developed by the United States in 1978. The technology quickly became the default for navigation devices worldwide, with 31 active satellites in orbit, of which only 27 are part of the GPS constellation, being active and available to use at any time. The rest of them are spare satellites that are ready to be activated if needed. GPS offers robust global coverage and is integrated virtually into every consumer device. It's built into everything, from smartwatches and logistics trackers to emergency response systems. While GPS transmits on multiple frequencies, using one improves accuracy to within 5 meters. Still, with dual-frequency receivers, mostly available in more modern devices, it can bring that down to less than a meter. This makes this technology a reliable, fast, and universally supported ally. But in isolation, GPS can fall short in environments such as dense cities or indoors, where signal propagation is complex and blockage becomes a real issue. Galileo, developed by the European Union, is a satellite navigation system that has been operational since 2016 and now comprises a constellation of 28 satellites. What sets Galileo apart isn't just accuracy, but how that accuracy is delivered. The system provides dual-frequency positioning and allows greater precision and improved signal performance. This quality in precision excels in complex environments like cities or mountainous regions. GLONASS, Global Navigation Satellite System, has been in operation since the 1980s and has modernized in the last 2 decades. Developed by Russia, this technology operates using 24 active satellites and offers full global coverage. But what makes it particularly interesting is its performance at high latitudes. Thanks to a unique orbital configuration, the GLONASS system maintains stronger signal stability in northern regions, such as Siberia or the Arctic. While it doesn't quite match the raw accuracy of GPS or Galileo, it holds its own when used alongside them. Devices that integrate GPS and GLONASS typically perform better in challenging environments such as forests or urban canyons, where line of sight to satellites can be compromised. The newest major entrant to the GNSS field is the BeiDou system, BDS, developed and operated by China. Officially achieved global coverage in 2020. Today is the largest satellite count system, with over 45 active. It's an impressive technology that's especially dominant in Asia-Pacific markets, where it not only delivers high-precision navigation but also includes two-way messaging and short-range communication features that other GNSS systems don't offer. While global integration is still underway, BeiDou is becoming a strategic asset in China's technological ecosystem, powering everything from smart infrastructure to logistics and military applications. For use cases centered in Asia, BeiDou might be the most responsive system available. The modern question in engineering is no longer which single system to choose, but how to best combine them. Multi-constellation receivers allow devices to synthesize signals from GPS, Galileo, GLONASS, and Beidou simultaneously. The rule of triangulation: the more satellites a device can see, the more refined its positioning becomes. In environments where tall buildings might block a GPS signal, a Galileo or GLONASS satellite might still be visible, ensuring the location pin remains steady. As we move toward an era of autonomous vehicles and hyper-accurate logistics, GNSS optimized design has become a critical necessity. The performance of any wireless device now hinges on its ability to navigate this invisible, multinational web of satellites. These devices simultaneously receive signals from GPS, Galileo, GLONASS, and Beidou, synthesizing them into a single high-accuracy result, proving that the Blue is a truly global achievement. From a simple scrolling paper map in 1932 to a global network of satellites guiding billions of drivers today, navigation technology has evolved dramatically. What once required careful map reading and guesswork is now handled by computers orbiting thousands of miles above the Earth. And yet, the goal remains the same as it was nearly a century ago: helping travelers find the right road. Thank you for joining us on this journey today. If you enjoyed this video, please don't forget to like, subscribe, and comment. We'd love to hear your thoughts in the comments below, so stay tuned for our upcoming features. We'll see you in the next one.